All right, so this is the second video for related rates in AP Calculus. I'm just going to go through a few more examples having to deal with related rates. And the last one we looked at was a business related rates problem. So we're going to look at another business problem here. We've got a company that manufactures sports supplements calculates that its costs and revenue can be modeled by the equations, and they gave us the cost function and the revenue function, where X is the number of units of sports supplements produced in 1 week. If production in one particular week is 1,000 units and is increasing at a rate of 150 units per week, find the following. So this 1,000 units, that's X, and then dx dt is 150. So we're going to use that all the way through. So A wants the rate at which the cost is changing. So we're only going to do the derivative with respect to time of the cost function. So the derivative of C is dc dt. The derivative of 125,000 would be 0. And then the derivative of 0.75x would be 0.75 dx dt. So then if we evaluate that for a rate of change of 150, the change in the cost would be $112.50, and time is being measured in weeks. So the cost would go up by $112.50 a week. So then part B wants the rate at which the revenue is changing. So we'll do the exact same thing, but we're going to do it using the derivative of the revenue function. So the derivative of 250x would be 250 dx dt. And then the derivative of minus 1/10 x squared would be minus 2/10 or 1/5 x dx dt. And then if we substitute our values in, we get 250 times 150 minus 1/5 times 1,000 times 150. And so the rate of change of the revenue would be $7,500 per week. So the revenue would also increase, but it would increase by $7,500 in a week. So if you know anything about business, the revenue is definitely increasing a whole lot faster than the cost is. Then for part C, it wants the rate at which the profit is changing. So again, if you know anything about business, profit is the revenue, which revenue is the total amount of money that you bring in. But then you have to subtract from it the amount of money it's costing you to do whatever it is you're doing, and that gives you the profit. So if we're wanting the rate of change of the profit, we would just take the derivative of that whole equation, and we would get dp dt equals dr dt minus dc dt. So we actually would just take our answer from B and subtract our answer from A, and we would end up with $7,387.50 per week. So that's how much our profit would increase by if we were able to sell 1,000 units a week and increase sales by 150 a week. All right, now, this type of related rates problem is super, super popular. They love to talk about ladders on the side of a house falling down the side of the house. I don't know why. It happens a lot, so maybe that's why. I don't know. So here we have a 25-foot ladder leaning against a house. The base of the ladder is pulled away from the house at a rate of 2 feet per second. So that would be down here. We'll call it the base. And so dB dt is 2 feet per second. Now, is that a positive 2 or is that a negative 2? Well, if you think about it, if you're pulling the ladder away from the house, that B length at the bottom is going to get bigger, which would mean its rate of change would be positive. So then it says, how fast is the top of the ladder moving down the wall when the base is? We've got different situations. So they're wanting to know the rate of change for our vertical length. So we'll call it H for the height. So they're asking us to find dH dt in all of these situations. Well, if the house was built correctly, this should be a right angle. And so now we've got three sides of a right triangle, all related somehow. Think about it. How are the sides of a right triangle related? That would be the Pythagorean theorem. So it's usually a squared plus b squared equals c squared, but I'm going to say b squared plus h squared equals l squared. So base plus the side of the house equals the ladder, like that. So that's the relationship, but if I want the rates of change, I've got to take the derivative of this relationship. So for each one of them, the derivative of b squared would be 2b db dt. H squared would be 2h dh dt. And L squared would be 2L dL dt. Now, dH dt is what I'm solving for, but I have right now a total of 6 variables in this equation. So I am crossing my fingers that all 5 of the other variables I know values for. So I'm going to start working my way through it. B, 7 feet from the house. So B is 7. dB dt is 2. They gave that to me. Then I come to H. I do not know what H is. But if I go back to my original Pythagorean theorem, b squared plus h squared equals l squared, b is 7 and l is 25. So I can actually solve that to figure out what h is. So I've got 49 plus h squared equals 625. H squared equals 576. And so h would actually be a perfect 24. No decimal or anything. So I can put a 24 right here. I do not know dH dt, but that's what I'm solving for. The length of my ladder is 25. Now, dL dt. dL dt represents the rate of change of the length of the ladder. Well, the ladder never changes its length. Even when it slides down the house, it's still 25 feet long. So dL dt is going to actually be 0 there. All right, so now you've got all your values filled in. You just have to solve for dH dt. So this would be 28 plus 48 dH dt equals 0. Subtract the 28. And so then when you divide by 48, you get dH dt equals negative 7 over 12, which is negative 0.583. And then the units would be just like they are for the base, feet per second. All right, so I want you to pause the video now, and I want you to give part B a try. Instead of the base being 7 feet from the house, I want it to be 15 feet from the house. I want you to solve for dH dt again with h being 15 feet from the house. So pause the video. All right, so check your math with my math. Over on the right-hand side in blue is where I've solved for h, now that b is 15. And then on the left-hand side, I continue to use that same 2b dB dt plus 2h dH dt equals 2l dL dt, substituted in my new values and solved, and I got negative 1.5 feet per second. Notice that in both A and B, my rates of change came out to be negative. If you think about it, that would be logical that they should be negative, because if my ladder is sliding down the house, then the height up the house is going to continue to get smaller until the ladder hits the ground. So since that height's getting smaller, its rate of change should be negative. Now, I want to continue to look at the ladder on the side of the house, but this time we want to find the rate at which the angle between the ladder and the wall of the house is changing when the base goes back to being 7 feet. So B is 7 feet. The rate of change of B is still 2 feet per second, and L is still 25. But this time what they want is the rate of change of the angle between the ladder and the wall of the house. So here's the ladder, here's the wall of the house. So this is what they're wanting the rate of change of. They're wanting us to find d theta dt. So So once you bring angles into it, it is no longer a Pythagorean theorem relationship with this right triangle. It is now a trigonometric relationship like sine, cosine, or tangent. So when you're trying to decide whether to use sine or cosine or tangent, I tend to like to use the things that I know. So I know for sure the value of B and the value of L because they were provided to me. So that's how I usually decide which ratio to use. So looking from theta, B is opposite the theta, and then L is the hypotenuse. So opposite and hypotenuse would tell me to use sine of theta. So sine of theta would equal B over L. So that's my equation that I'm going to use, which means that's what I'm going to take the derivative of. So the derivative of sine theta is cosine theta, but then I'm going to multiply it by d theta dt. To get the derivative of the right-hand side, I have to do quotient rule. So bottom times the derivative of the top. The derivative of B is dB dt minus the top times the derivative of the bottom. So that would be dL dt. And then all over the bottom squared. So now this is what I want to be able to plug in for. I have 1, 2, 3, 4, 5, 6, 7 unknown things in there and not a single number. So I've got to replace 6 of those 7. The only one that I don't know and that I can't know is d theta dt. So I should be able to substitute everything else with a value, including cosine of theta. So cosine is adjacent over hypotenuse. So cosine of theta is going to be h over L, but I need those actual values. The latter is 25, and if you go back and look at example 7 part A, when the base was 7 feet, as they're giving us here, that height was 24. So my cosine theta is 24 over 25. And then that's times d theta dt equals L, which is 25, times dB dt, which is 2, minus B, which is 7, times dL dt, which is still 0, because that ladder is not changing in length, over 25 squared. So now I've got all those numbers in there. I just have to solve for d theta dt. So I've got 24 over 25 times d theta dt. So I'm going to simplify this fraction on the right here. So 25 times 2 is actually 50 over 625. But what I'm actually going to do is I'm going to cancel a 25 out of both of these. So that becomes 2 over 25, because the 7 times 0 just becomes 0. So then d theta dt, if we divide the 24 over 25 over, that means we multiply by the reciprocal of it. Notice those 25s cancel, and so we get 2 over 24, or 1/12. Now, we need some units. So I told you in the first video that when you're trying to come up with units, pay attention to the fraction in the rate of change. So theta over time. So what do we measure theta in? Well, theta is an angle. You are in calculus class, not physics class. What do we measure all of our angles in calculus class? We measure them in radians. And then the time, if you look at the other times in this problem, is in seconds. So that's 1/12 of a radian per second for that problem. Angle problems are also extremely popular.